A mountain range, older than most complex life on land, still dominates the eastern horizon of North America, its ridgelines stretching for thousands of miles, while quietly shifting, adjusting, and responding to forces deep within the Earth. How does a landscape forged more than 480 million years ago remain so prominent today? Why do some of its peaks still rise sharply above surrounding valleys instead of fading into low hills? And what unseen processes continue to alter terrain that, by conventional expectations, should have long ago eroded into near-flat plains? Overlooking the foothills of the Great Smoky Mountains in eastern Tennessee, a common question emerges. Why do such large mountains still exist within the ancient Appalachian Mountains? From near Gatlinburg, Mount LeConte rises to about 6,593 feet above sea level, equivalent to roughly 2,010 meters. With Gatlinburg sitting at approximately 1,300 feet, or about 400 meters, the climb to the summit represents more than a mile of elevation gain across a horizontal distance of about 6 miles, close to 10 kilometers. This gradient ranks among the most pronounced elevation changes anywhere in the Appalachian system. While the range extends from the southeastern United States into New England, few locations exhibit terrain as steep and rugged as that found within the Smokies. Although the geologic events responsible for building the Appalachians occurred hundreds of millions of years in the past, the present-day landscape retains a striking degree of relief. High-resolution digital elevation models reveal peaks surpassing 6,000 feet, approaching elevations near 2 kilometers. In certain sections, the vertical difference between valley floors and nearby summits approaches a mile, or about 1.6 kilometers. These measurements challenge the assumption that extreme age inevitably leads to subdued topography. Within the southern Blue Ridge Mountains lies what can be described as the structural and topographic core of the range. This region contains some of the highest elevations and the most rugged terrain. Yet these mountains are no longer forming in the way they once did. Their origin traces back to a period when tectonic plates converged, compressing and thickening the Earth's crust to create a massive mountain system. That system, once comparable in scale to modern ranges such as the Himalayas, formed during the assembly of the supercontinent Pangaea. At that time, continental collisions forced vast sections of crust upward, while simultaneously driving material downward into the mantle. The resulting structure included not only towering peaks, but also an extensive route beneath the surface. This route extended deep into the Earth, providing structural support for the elevated terrain above. The subsequent breakup of Pangaea, beginning roughly 200 million years ago, dramatically altered this configuration. As tectonic forces shifted, the landmass that would become North America began to separate from what are now Africa and Europe. This process initiated the opening of the Atlantic Ocean and effectively split the original mountain system. The eastern portion of the range was carried away with the separating continents, leaving behind only part of the original structure on the western side. Today's Appalachians represent this remnant. In regions such as the Appalachian Piedmont, rocks similar to those found in the mountains are present, yet they do not form prominent peaks. This contrast highlights how much of the original mountain system was either removed or repositioned over geological time. What remains is not a complete mountain range in the original sense, but rather a surviving fragment of a once much larger formation. Beneath this fragment lies a key factor in the persistence of elevation, an unusually thick section of continental crust. In some areas, the crust beneath the Appalachians reaches depths of up to 30 miles, or about 48 kilometers. By comparison, crust nearer to the Atlantic coast may measure closer to 20 to 25 miles, or roughly 32 to 40 kilometers. This difference in thickness plays a fundamental role in maintaining the height of the mountains. The behavior of this thickened crust can be compared to that of an iceberg floating in water. The larger the portion submerged below the surface, the higher the visible portion can rise above it. In geological terms, this concept is known as isostatic balance. As erosion gradually removes rock from the surface, reducing the overall mass of the mountains, the crust responds by slowly rising. This uplift does not represent new mountain building in the traditional tectonic sense, but rather a compensatory adjustment that helps preserve elevation over long periods. Erosion itself operates continuously across the Appalachian landscape. Rainfall, river flow, temperature changes, and chemical weathering all contribute to the breakdown of rock. Over millions of years, these processes should theoretically reduce even the tallest mountains to low-relief terrain. However, the rate at which erosion occurs is not uniform, and several factors act to slow it in key areas. River systems provide one of the most significant controls. In many portions of the Appalachians, especially those draining toward the Gulf of Mexico, rivers follow long and indirect paths before reaching sea level. These extended routes reduce the gradient of the rivers, limiting their ability to carry away large volumes of sediment quickly. As a result, erosion proceeds at a slower pace, allowing higher elevations to persist. By contrast, rivers that flow directly toward the Atlantic Ocean often have shorter and steeper paths. These conditions increase their erosive power, enabling them to remove material more efficiently. This difference in drainage patterns helps explain variations in topography across the range, with some regions experiencing more rapid landscape reduction than others. Rock composition further influences how the mountains evolve. The highest peaks in the Great Smoky Mountains are composed largely of quartzite and metamorphic rocks derived from sandstone. These materials are highly resistant to weathering and erosion. Their durability allows them to withstand environmental forces that would more quickly break down softer rock types. In practical terms, this means that certain ridges and peaks persist not because they are being uplifted rapidly, but because they erode more slowly than the surrounding terrain. Over time, areas composed of weaker rock are worn down at a faster rate, leaving behind the more resistant formations as elevated features. This process contributes to the rugged appearance of the landscape, even in the absence of active mountain building. Beyond surface processes, activity within the deeper lithosphere also plays a role. In some cases, dense sections of the lower lithosphere can detach and sink into the mantle. When this occurs, it effectively removes weight from beneath the crust. The overlying material responds by rising slightly, similar to how a floating object rises when a weight is removed from below it. This mechanism, though subtle, can contribute to long-term elevation changes. It does not produce dramatic increases in height over short timescales, but over millions of years, even small adjustments can influence the overall structure of the landscape. Such processes illustrate that the Appalachians are not static features, but dynamic systems influenced by forces both at the surface and deep within the earth. Time remains a critical factor in understanding the current state of the range. The initial formation of the Appalachians began more than 480 million years ago. Major phases of mountain building occurred over tens of millions of years as continents collided and merged. Following the breakup of Pangaea, the range entered a prolonged period of erosion and adjustment that continues to the present. Despite approximately 270 million years since the peak of their formation and about 200 million years since the continents began to separate, the Appalachians retain a level of topographic prominence that appears inconsistent with their age. This persistence reflects a balance between competing processes, erosion working to reduce elevation, and various forms of uplift and resistance working to preserve it. In regions like the southern Blue Ridge, this balance is particularly evident. The combination of thick crust-resistant rock types and less efficient river erosion has allowed significant relief to remain intact. These conditions create landscapes where steep slopes, high peaks, and deep valleys coexist within an ancient geological framework. At the same time, the range as a whole continues to change. Measurements of river incision, sediment transport, and subtle deformation indicate that the landscape is still evolving. Movements may be slow, often occurring at rates measurable only over extended periods, yet they are continuous. The idea that these mountains are entirely dormant does not align with the evidence of ongoing change. Across the Appalachian region, the interplay between structure, composition, and process produces a complex and varied terrain. Some sections appear subdued with rolling hills and wide valleys, while others retain sharp ridges and significant elevation differences. This diversity reflects differences in underlying geology, as well as the cumulative effects of millions of years of environmental interaction. The persistence of features such as Mount LeConte underscores the importance of local conditions. Its height relative to surrounding areas is not simply a remnant of past scale, but the result of multiple factors acting together over vast spans of time. The mountain stands as an example of how ancient formations can maintain prominence when geological circumstances align in their favor, even as erosion continues and rivers gradually reshape the land. The fundamental structure of the Appalachians remains influenced by its deep roots and historical development. The range does not grow in the way it once did during continental collisions, yet it has not reached a state of complete equilibrium either. Instead, it occupies an intermediate condition where change is constant but often subtle. Measured against human timescales, these changes are nearly imperceptible. However, within the context of geological time, they represent an ongoing evolution. The Appalachians, though ancient, are not relics frozen in place. They continue to respond to internal and external forces, maintaining their presence through a combination of resistance, adjustment, and structural inheritance. The persistence of the Appalachian Mountains becomes even more striking when viewed through the lens of long-term landscape evolution, where multiple systems interact over immense spans of time rather than operating in isolation. The range that exists today is not simply an eroded remnant of a once towering mountain chain, but a continually adjusting structure shaped by the balance between removal and renewal, surface processes and deep earth dynamics, resistance and gradual change. One of the most critical aspects often overlooked is the concept of dynamic equilibrium within the landscape. Although erosion continuously lowers elevations by removing material, this process does not proceed unchecked. As rock is stripped away from the surface, the reduced weight allows the underlying crust to respond. This response is gradual but persistent, involving vertical adjustments that partially offset the loss of material above. The result is not a static system, but one in which lowering and uplift occur simultaneously, maintaining relief over far longer periods than would otherwise be possible. This interaction becomes particularly evident when examining long river profiles across the Appalachian region. Rivers act as the primary agents of erosion, cutting into rock, transporting sediment, and ultimately delivering that material to distant basins. However, their efficiency is strongly controlled by gradient, discharge, and path length. In regions where rivers must travel hundreds of miles or several hundred kilometers before reaching sea level, their ability to erode deeply into the landscape is reduced. The energy available for downcutting is distributed across a longer distance, resulting in more gradual lowering of the terrain. In contrast, shorter river systems draining directly toward the Atlantic Ocean often display steeper gradients. These conditions enhance their capacity to incise into bedrock, accelerating erosion locally. This difference creates an uneven pattern of landscape evolution where some sections of the Appalachians are worn down more rapidly, while others retain higher elevations. Over time, this imbalance contributes to the preservation of rugged terrain in specific areas, particularly within the southern portion of the range. Another factor reinforcing this persistence lies in the internal composition of the mountains themselves. The geological history of the Appalachians involved multiple phases of sediment deposition, metamorphism, and deformation. These processes produced a complex arrangement of rock units with varying resistance to weathering. Quartz-rich formations, including quartzite and certain metamorphic sandstones, exhibit exceptional durability. Their crystalline structure makes them less susceptible to chemical breakdown and physical fragmentation. As erosion progresses, weaker rocks such as shale or less resistant sedimentary layers are removed more quickly. This selective erosion enhances topographic contrast, leaving behind ridges and peaks composed of stronger materials. Over millions of years, this process amplifies relief rather than eliminating it entirely. Instead of smoothing the landscape uniformly, erosion sculpts it, emphasizing differences in rock strength and structure. The structural architecture of the Appalachians also plays a significant role. Folding and faulting during ancient tectonic collisions created a series of aligned ridges and valleys. These structures influence modern drainage patterns, guiding rivers along zones of weakness while leaving more resistant areas elevated. The repeating pattern of ridge and valley topography, especially prominent in regions like Pennsylvania and Virginia, reflects this inherited structural framework. Beneath the surface, deeper processes continue to influence the elevation of the range. One such process involves the behavior of the lithosphere, the rigid outer shell of the Earth. Over time, portions of this layer can become denser due to cooling or compositional changes. In certain conditions, these dense segments detach and sink into the underlying mantle, a process sometimes referred to as lithospheric removal. When such detachment occurs, it effectively reduces the weight acting on the overlying crust. The result is a slow upward adjustment, adding a subtle but measurable component of uplift. While this mechanism operates over timescales far beyond direct observation, its effects accumulate, contributing to the long-term maintenance of elevation across parts of the Appalachian region. Thermal influences within the Earth also contribute. Variations in heat flow beneath the crust can affect its buoyancy and mechanical behavior. Warmer regions tend to be less dense and more capable of sustaining higher elevations. Although the Appalachians are not associated with active volcanism in the present day, residual thermal anomalies from past tectonic events may still influence the structure and stability of the crust below. Surface conditions further complicate the picture. Climate exerts a powerful control over erosion rates through precipitation, temperature fluctuations, and vegetation cover. In humid regions like the southeastern United States, abundant rainfall promotes chemical weathering, gradually weakening rock and making it more susceptible to removal. At the same time, dense vegetation can stabilize slopes, reducing the rate of physical erosion by limiting direct exposure of soil and rock. Seasonal variations also play a role. Freeze-thaw cycles, though less intense than in colder climates, still contribute to the mechanical breakdown of rock in higher elevations. Water entering cracks expands upon freezing, gradually widening fractures and facilitating further weathering. Over extended periods, these incremental changes accumulate, shaping the smaller features of the terrain. Sediment transport provides another layer of insight into the ongoing evolution of the Appalachians. Material eroded from the mountains does not simply disappear. It is carried downstream and deposited in basins, floodplains, and coastal environments. The volume and distribution of this sediment offer clues about erosion rates and landscape change. In many cases, sediment accumulation along the Atlantic coastal plain reflects the long history of material being stripped from the mountains and relocated over vast distances. Despite this continuous removal, the rate at which sediment is produced does not outpace the mechanisms preserving elevation. This balance underscores the resilience of the system. It is not that erosion is weak, but rather that it is counteracted by a combination of structural, compositional, and deep processes that collectively sustain the landscape. Geophysical measurements provide further evidence that the Appalachians remain active in subtle ways. Modern techniques such as satellite-based positioning systems can detect minute vertical and horizontal movements of the crust. These measurements reveal that parts of the range are still undergoing slow uplift or adjustment, even in the absence of active plate boundary interactions. The magnitudes involved are small, often measured in fractions of an inch per year or a few millimeters annually, but over millions of years such rates are sufficient to influence overall topography. Seismic activity, though relatively low compared to tectonically active regions, also indicates that the crust is not entirely stable. Occasional earthquakes within the eastern United States reflect the presence of stress within the crust, remnants of ancient tectonic forces that have not fully dissipated. These stresses can contribute to minor reactivation of faults, subtly altering the structure of the land over time. The idea that the Appalachians are still moving does not imply dramatic change or rapid uplift. Instead, it reflects a continuous state of adjustment, where the landscape responds to both internal and external forces. The mountains are not rising in the sense of active mountain building seen in younger ranges, but they are also not simply eroding away without resistance. They exist within a dynamic balance that allows them to persist far longer than might be expected based solely on their age. This persistence challenges conventional assumptions about geological age and landscape evolution. It demonstrates that the longevity of mountain systems depends not only on when they formed, but also on the conditions that govern their subsequent development. In the case of the Appalachians, those conditions have aligned in a way that favors endurance, from the thickness of the crust beneath them to the composition of the rocks at their peaks, from the paths of their rivers to the processes operating deep within the mantle. Every component contributes to a system that remains active, interconnected, and responsive. The result is a mountain range that continues to exhibit significant relief despite having formed hundreds of millions of years ago. As observations and measurement techniques continue to improve, the understanding of these processes becomes more refined. Data collected from satellite monitoring, river analysis, and subsurface imaging reveal a landscape that is far from static. Each element, from the smallest grain of sediment to the deepest portion of the crust, plays a role in shaping the ongoing evolution of the range. If you found this breakdown clear and informative, consider supporting the channel by liking the video, sharing it with others who are curious about Earth science, and subscribing for more in-depth content. Tap that hype icon as well to help this video reach a wider audience and keep more detailed geology content coming.